Welcome back, Night Owls. This is Dr. Nighttime. And tonight we're continuing with my LTAM course. And we're getting into a supplementary video for Chapter 2. If you remember, over the past couple videos, I talked about how while calculating curtailed expectation of life can be a little tedious, and that I would present an approximation technique. Here I'm presenting that approximation technique, and that's entirely what this video is about. It's called Woolhouse's approximation, or the Woolhouse approximation, or the Woolhouse formula. And while the LTAM doesn't require it for curtailed expectation of life specifically, they do require it for stuff that gets a little more complicated. Once money starts getting involved, and rather than it being a person surviving for some amount of time, it's a person making annual payments or monthly payments, and trying to address money getting involved, and so you have to worry about interest. That makes all the calculations that much harder. So rather than trying to introduce it for the first time when you're in the middle of looking at that, I figured if I introduce this tool here, that would probably make it easier to manage understanding that formula in that more complex case when it comes up. So LTAM doesn't actually make you know this until around Chapter 5, but I figure I might as well introduce it here. So consider the case of curtailed expectation of life. Suppose you have an exponential survival model, or a constant force of mortality survival model. So suppose you have a piece of equipment with an exponential future lifetime with mean 10 years. Note that this is the same as constant force of mortality being 0.1. Hopefully that's intuitive to you by this point. Suppose you have to find the curtailed expectation of life. So it should be no surprise that the survival function would be e to the negative t over 10, and that the complete expectation of life would be 10 years, or at least if you do the integration, you should get that it's 10 years. So we know that the curtailed expectation of life has to be a little bit less than 10 years. And you can express curtailed expectation of life as the infinite sum, e to the negative 0.1 plus e to the negative 0.2 plus e to the negative 0.3, etc., etc., etc. Now we realize that this is a geometric series. And using the formula for sum of a geometric series, crunching it in on a calculator, we get curtailed expectation of life is 9.50833375. Now, that's an awfully large number of significant figures. The reason I'm reporting it to that many significant figures is because that's about how many significant figures you need to get a sense of scale of the error in the approximation technique that I'm about to mention. Whenever you do an approximation, there's going to be some error. The error is small enough that you really do need that many significant figures to get a sense of how big the error is. So when we think about relating a sum to an integral, one thing that may come to mind is Riemann sums from calculus. And how you can take a limit of Riemann sums to find an integral. Here we're using it in reverse. We're saying, if I know the integral, can I estimate the Riemann sum for a fixed step size? In this case, step size 1 year. Later on in Chapter 5, we'll also talk about varying the step size. But for now, step size is just going to be fixed 1 year, and it will be throughout the video. So what do I have here? I have a graph. What's it a graph of? Well, this red curve here, that is an exponential decay curve. These green steps, I'll call it green staircase, that is the right Riemann sum with step size 1. Note that to do curtailed expectation of life, you're essentially taking a right Riemann sum with step size 1. Okay. What are these blue things? As the title of this slide suggests, the blue things are the trapezoids of trapezoidal rule, or trapezoidal approximation. So, if I pretend for the moment that the integral is exactly equal to its trapezoidal approximation, it's an approximation, then I can say that the Riemann sum staircase is equal to the trapezoidal approximation, or the integral, right, because we're temporarily assuming they're equal, and subtracting off the triangles. Alright, so how big are these triangles? Well, they all, formula for a triangle, area of a triangle is 1/2 base times height. Each base is 1 year. This height is survival at 0 minus survival at 1. This height is survival at 1 minus survival at 2. Then survival at 2 minus survival at 3. Etc., etc., etc. So I get that the complete expectation of life is approximately curtailed expectation of life plus 1/2 survival at 0 minus survival at 1 plus survival at 1 minus survival at 2, etc., etc. This telescopes down to curtailed expectation of life minus 1/2 survival at 1, or sorry, plus 1/2 survival at 1 minus survival at infinity, or sorry, survival at 0 minus survival at infinity. Survival at 0 is always 1. Survival at infinity is always 0, right? If you remember those from the properties of a valid survival function. So that means we get complete expectation of life is curtailed expectation of life plus 1/2, approximately. Tells us curtailed expectation of life is approximately complete expectation of life minus 1/2, or in this case, 9.5. This is what's called the two-term Woolhouse approximation. One modification, suppose that instead of wanting e sub x, you wanted e sub x colon angle n. Well, so suppose I want to stop, excuse me, suppose I want to stop after 4 years. Then instead of saying s of 0 minus s of infinity, it would be s of 0 minus s of 4. So what you get is complete expectation is approximately curtailed expectation plus 1/2 survival at 0 minus survival at 4, or n, or however many years I decided to count. Alright, so that's the two-term Woolhouse approximation. Now, as you've noticed, this is equivalent to saying, well, just subtract half a year from complete expectation to get curtailed expectation. And typically, the problems they'll give you on LTAM specifically want you to go a little more in depth than that. That's okay. I talked about this as the two-term Woolhouse approximation. Here I say first two terms. What goes into the third term? The third term accounts for the derivative of the survival function. And if you were to match, let me go back one slide. Here, I'm approximating this red curve by just connecting the dots in straight lines. What if instead of just connecting straight lines, I had to match the value at the endpoints, at the endpoint of each segment, so here to here. I had to match the value here, and slope here, and slope here. There would be a unique cubic that would do that. I have 4 conditions: value and slope at each endpoint, and 4 terms in the cubic. So I match my 4 equations to my 4 unknowns. I can uniquely determine the cubic. It'll be one cubic function here, then it'll change and be a different cubic function here, then it'll change and be a different cubic function here, but they'll all smoothly spline into each other. So that's the technique we use. Now, there's a lot of math that goes on here. This is going to be a 2-slide derivation. The only part of the result you need to know is in big letters at the end of next slide. So if you want to skip this slide and the next, okay. For those of you who want to know where this comes from, here it goes. we assume that the spline is equal to the trapezoidal function plus some cubic function g of t, where g of t obeys the fact that g of 0 is 0, right, since it's the correction, right, you're not introducing any correction at the endpoints. G of 0 is 0, g of 1 is 0, and the derivatives have to match, but the trapezoidal approximation has some slope, we'll call that k. So say that g prime at 0 is s prime at 0 minus k, and g prime at 1 is s prime of 1 minus k. We said g was cubic, so it has this form. Now we said g of 0 is 0, so d must be 0, and g of 1 is 0, so a plus b plus c must be 0. So that gets us this formula, where we've got g of t written only in terms of the two unknowns a and b. We differentiate to get g prime, and we use the fact that g prime of 0, so we get g prime of 0 as negative a minus b, we get g prime of 1 as 2a plus b, just if we plug in the numbers. And solving this system of two equations and two unknowns, we'll get that a and b must equal g prime of 0 plus g prime of 1, and negative 2g prime of 0 minus g prime of 1, respectively. If we want the area to approximate the integral, so the integral of this spline, we do our calculus, integrating from 0 to 1, we get it's 3a minus 2b over 12. Substituting in what we said a and b were, that gets us g prime 0 minus g prime 1 all over 12. And that means that the area added, again, this is the difference between the spline and the trapezoid. This is that added g function. This is the extra that the g gives you. That would be s prime of 0 minus s prime of 1 all over 12. That's the piece you'd need to know. Actually, you don't even need to know that, but this makes it an easy one step for what you need to know. And this helps you visualize, okay, if my function is curving, this is how the curvature affects the approximation. I can say 1/12 difference of derivatives. Because now what I'll say is complete expectation of life is approximately Curtate expectation plus trapezoidal correction, right, the 1/2 difference of survival functions, plus 1/12 difference of derivatives of survival functions. And so in the event that I'm going all the way out to infinity, I'm not doing a colon angle n, then I get complete expectation equals Curtate expectation plus 1/2 survival function at 0 plus 1/12 derivative of survival function at 0. And survival function at 0 is always going to be 1. Derivative of survival function at 0 is not. Here, you have to actually differentiate the survival function. In this case, it's negative 0.1. And we get this expression. Do the algebra. We get Curtate expectation of life is approximately 9.50833333. We said the actual answer was 9.50833375. So as we can see, this is a pretty darn good approximation. And I'll just add in, if you have a colon angle n situation, then we'll say that complete expectation equals Curtate expectation plus 1/2 survival at 0 minus survival at n plus 1/12 derivative survival at 0 minus derivative survival at n. And it's only in the limit as n goes to infinity that the survivals at n go to 0. Notice that derivative of survival function for large n should go to 0. Just because when you don't have very many total people surviving that long to begin with, the rate of change should also be 0, or close to it. One issue that you can run into, what if you have a vertical tangent? So before, when I said you can always uniquely determine a cubic function that will match the value and slope over an interval, I lied a little bit. If there's a vertical tangent, there's no cubic function that ever has a vertical tangent somewhere. So if right at the endpoint you have a vertical tangent, you can't fit a cubic to that. And my recommended fix, just pretend that you're excluding that 1 year, and then add in the probability for just that 1 year manually. Because what makes curtailed expectation so tedious is that you have to account for many years manually, one at a time. Doing a calculation then adding in the term for 1 year shouldn't be a problem. And in an example I'll go through, I'll show how you handle that. So let's revisit problem 2.1. If you like, you're welcome to pause this video and solve through this problem using that approximation technique. I'll go through it momentarily. So, again, you're given a survival function and the force of mortality, and again we had to solve for omega and found that omega equals 110. And now suppose we wanted to calculate the curtailed expectation of life at age 106 using the 3-term Woolhouse formula. Okay, finding omega is still the same. We would say curtailed expectation is approximately complete expectation minus 1/2 survival at 0 minus survival at 4, plus 1/12 survival prime at 0 minus survival prime at 4, because 4 is the maximum number of years that a person can survive. But looking back at that formula, we actually have a vertical tangent at t equals 110, which would mean 4 years from when you're measuring when the person's 106. So what I actually have to do is say, let's pretend we wanted curtailed expectation just up to 109, and then add in survivors to age 110 separately. And what we can get away with here is pointing out that survival of 106 at time, or 4 years into the future, is 0 anyway. So this piece that we're adding in is just a 0. If it weren't 0, then we would just add in something else, or whatever it would be. It's just a matter of plugging into the survival function. But now we can just ditch this term because it's 0 anyway. If it weren't, we would just separate it out. Again, the reason why we have to separate it out is because of the derivative term here, and that would be infinite, and that would make unpleasant things happen in our function. So, I can say that curtailed expectation, that complete expectation, if I were only going up through 3, then the complete expectation would be 2.634 when you do this calculus and take this integral. Plugging in for the survival functions, for the second term we get an 0.146, and then for this third term, that's going to involve the derivative of the survival function. So here we go, I just differentiate it, this is what you get. And when you plug that in, you get 0.00952, rounds to 0.010. Crunch your numbers in and you get that that curtailed expectation is approximately 2.478. Compared to the 2.48 that we got without the approximation. And yeah, we would have gotten the answer right. Now, this is more work than just summing for the 107, 108, and 109-year-olds. But suppose that they wanted not curtailed expectation of 106, but say curtailed expectation of 90. This approximation would still work just fine. and you'd still do exactly the same amount of work. Even though you'd have to account for 20 years. So you'd be avoiding needing to take a 20-term sum. Not that LTAM is going to ask you to do a 20-term sum, but it's a technique, might as well present it. One last problem I'd like to go through. Let's revisit problem 2.4, but pretend that instead of asking for complete expectation of 75 colon angle 10, what if they wanted curtate expectation 75 colon angle 10? Well, first term in the Woolhouse approximation says you should take complete expectation 75 colon angle 10. So you'd have to take this integral anyway. So you essentially have to solve the actual problem 2.4. I'm assuming you remember how to do that. Here they give us the survival function at time 0. This is the survival function at time, this is the survival function for a newborn. This is the survival function for a 75-year-old. Hopefully that's not too much trouble for you. We can say that curtate expectation of 75 colon angle 10 is going to be this integral for complete expectation minus 1/2 S75 of 0 minus S75 of 10 minus 1/12 S prime 75 of 0 minus S prime 75 of 10. And crunching all our numbers together and taking our derivatives, the final answer we get here is 8.0262. So if you recall, the complete expectation of life is like 8.20 something. Curtate expectation is like 8.02. Now, one thing you'll notice, typically we say curtate expectation is about half less. Here it's significantly less than half less, right? It's less by like 0.18, not by 0.5. The reason is you only subtract half a year per person who dies, and that you have a significantly higher survival rate from 75 to 85 than 0%. So that's the introduction to the Woolhouse formula. We'll get more into that in Chapter 5. Just want to get our feet wet here so that it's less of a leap and less of a stumper when Chapter 5 rolls around. As always, if you like the way I explain things and want to arrange private lessons, click the link in the description below. Until next time, this is Dr. Nighttime wishing you a good night.